Alright? But you can probably see where I'm going with this now. Now post multiply by A inverse. So we'll get A inverse equals B inverse A inverse. Right? Well, that's E. So you're just left with AB equals, hold on, what am I doing? I'm confusing myself. I think I'm getting tired. That was a different proof. Okay, so I'll pay more attention to what I've written in my actual notes. Okay, so let AB, oh God. Let AB equal X, right? Square both sides, AB squared equals X squared equals E. That's before. Now multiply both sides by A, so you'll get A into AB, AB equals A. Okay? So this is A squared BA, B equals A. Okay. And A squared is E. A squared, that's just E. So then you've got BA, B equals A. Now, post multiply by B on both sides. So you get B squared equals AB. Let's get rid of these. Alright, now B squared's, from here, B squared is E. So you've got BA is AB, is AB, is AB. Can't even write it. Okay, so BA equals AB, so we've proved that. Alright, let's see. You're asked to, now 1, 2, 3, 4. 4 examples of candidates for groups, and you're to say whether they are a group or not. Okay? Now if you think it's not a group, all you have to do is just find one part of the four criteria that is not satisfied, and then you can rule it out as a group. It's not a group. But if you think it is a group, then you have to go through all 4 criteria. Okay. Okay, here's the first one. The set of all odd integers under addition. So if you add 2 odd integers, you get an even integer, right? But that's not an odd integer. So the result does not belong to the original set. So immediately it's not closed. Okay, so it's not closed. It doesn't satisfy one of the 4 conditions, so therefore it's not a group. So the set of odd integers under addition is not a group because it's not closed. Okay. Okay, second one. You've got the set of all integers of the following form. Now I've got to find a dry patch. 2 to the m. Maybe I'll try another pen, see if that helps. So 2 2 to the, oh yeah. So 2 to the m, 5 to the n. That's the form. You've got the set of all possible integers of this form. Okay? And the binary operator is just multiplication. Now, is that a group? So your set is, you know, all integers of that form. So you know, power of 2 times power of n, and m and n. What are they? They're just integers, right? So they can be positive or negative, just integers. Is that a group? Now if you multiply them, any 2, so 2 to the m, 5 to the n times 2 to the p, 5 to the q of that form, where p and q are also just integers. Well, that's of the form m plus p, 5, n plus q. Right? Now these are integers, so this is of the same form as that, so therefore closed. So that's okay. Right? So closure works for this set, and the binary operator is just multiply. Okay, so how about associativity? Well, integers, in powers of integers, are themselves associative, right? So associativity works. So you know, you take any 3 of these, you'll just get, well, here's, we have 2 of them, but if you had 3, you'd have 3 of these exponents. And so associativity works, so that's okay. How about the unit? What would the unit be? Well, if m equals n equals 0, you've got 2 to the 0 times 5 to the 0. Well, that's just 1 times 1, which is 1. Okay? And if you multiply an integer by 1, you just get the integer. So the unit is when m and n are 0. Okay? So we've got a unit. That's okay. Now how about inverse for each of these? All right. So if this is your general element, 2 to the m, 5 to the n, well, the inverse would just be this, right? Now that's okay, because you know, just the minus of it. These are still integers, because z can be plus or minus integers, or 0. Okay, so if you multiply that by that, of course you'll get 1, right? So for each element there's an inverse. We've got a unit when m and n are 0. We've got associativity, because that's the general property of integers. And we've got closure, because you know, the product is of the same form. Therefore, this set and binary operator multiplication is a group. It is a group, right? So that is a group. All right. All right. The two. You know, I need some space. Just a minute. I need some space. Now this next question, it's a matrix type question. You're asked whether a particular matrix form is a set of them is a group or not, and obviously the binary operation for matrices would just be matrix multiplication. You just multiply 2 matrices together. So it depends, the answer whether it's a group or not depends on the type of matrix that it is. Some sets of matrices are groups, others aren't. And the whole, the set, dealing with matrices is a major part of group theory. A lot of theory and a lot of examples about it. Okay, so here's you've got a set of matrices, and they take the following form. A, B, naught, naught. And what are A and B? A and B are reals. A and B are reals. They belong to the reals. Okay. Now let's try and prove it's not a group first, because that's easy. You only have to find one little piece, one part of the 4 criteria that's not satisfied, and then you can reject it as a group. Well, I just look at this and say there's no way with that type of matrix that you could ever get this, right? Because this is 0, this is 0. But if I'm going to have a unit matrix, because I'm multiplying matrices, if I'm going to have a unit matrix, I have to have a 1 here. But that's excluded, right? Because these two positions here have to be 0. So immediately I know with this set of matrices of this form, 2 by 2, A, B, naught, naught, I cannot have this kind of matrix, and I need that for the unit matrix. So the unit matrix is excluded. So there's no unit, and therefore one of the 4 criteria to be a group is not satisfied. There's no unit. Now a group has to have a unit, and there is no unit. This form is incompatible with this. So there's no unit, therefore this set of matrices of that type is not a group. So not a group. Okay, so next one, a bit more subtle. Okay, you have to pay attention a bit. I hope this is dry by now. So part 4 of question 9. So 9 part 4. Again, it's a 2 by 2 matrix type question. So you've got the set of matrices A, naught, B, C. So it's the set of all matrices of this form. Now you're told that A and C are reals. Okay, so the 2 diagonal terms, A and C, they're both real, and they're both non-zero. A and C both non-zero. Okay, you're told that. And B here is a rational.